Yeah, sorry about that. My computer froze there, but we had pretty much finished talking about simple series circuits. So let's pick up here with this picture, which is showing us an animation of two resistors in parallel. So what's going on here is the battery's doing the same thing it always does, raising the charge, giving them energy. Then they go down these wires, and now what happens is you have a branch point, right? That's what defines circuits being in parallel, is that elements in the circuit are on different pathways, right? It's not that they are geometrically on parallel lines, although they're frequently represented that way, but they don't have to be. It's that they are different paths, right? The charges that go down this path do not go through the 10 ohm resistor, and the charges that go through this path do not go through the 30 ohm resistor. So that gives you one of the rules right away for parallel circuits, and that is that the current is different, right? The 30 ohm resistor is 3 times harder to get through. So if you look and count the number of charges going through here per second, you should find that is roughly 1/3, right? The 10 ohm resistor is getting 3 times the current going through it. And the 30 ohm resistor, and that should make sense to you, right? And if you back up to here to the split point, this is the junction right here, the charges coming in there has to be enough current coming into this junction to supply this pathway and that pathway together, right? But, and here's the other rule, each of these pathways individually are connecting this plateau, this height, down to this height, right? And so that you will measure and you will find that the voltage difference for each parallel path is the same as each other, right? And so those are the rules for parallel circuits. Here's a schematic for it. I mean, there's lots of different ways you could draw it, but basically you do need to have some kind of junction point, and then R1 and R2, and then they have to come back together at some point after that. Like I said, they don't actually have to be drawn on parallel lines, but it makes the schematic look a lot cleaner. In reality, of course, if you open real-world circuits, you'll see the wires are just look like a rat's nest in there. But if you straighten them all out and attach them at right angles and stuff like that, then you can kind of get the schematic back. And so let's see, in this picture they're making R1 just slightly bigger. It looks like 20% bigger than R2. And so I don't know why they did that, because it makes it very hard to see the difference between the two currents. But nonetheless, that's what we have here. So now you've seen resistors in series and resistors in parallel, but of course it is also possible to hook up your resistors in such a way that not all of the resistors are in simple series with each other or in simple parallel with each other. So for instance, here you have 3 resistors, R1, R2, and R3, and they are not all 3 on different paths, and they are not all 3 on the same path, right? And so you cannot categorize this as a series or parallel circuit. Instead, it's a combo or a complex circuit, right? What you do in situations like this, though, is you have to look for overall trends. So there is a junction up here right before R1, right? And there are 2 pathways that are in parallel, right? There aren't 2 resistors in parallel, but 2 pathways. So for instance, one pathway is this one that contains only R3. The other pathway in parallel contains R1 and R2 in series with each other, right? And so by describing the problem this way, we see how we can break this down, right? We can apply the rules for series circuits within this single pathway. R1 and R2 are in series with each other, so they will obey all the rules of series circuits. Like, for instance, they have to split up this voltage, and they have to have the same current, right? And then once we deal with that pathway, where we can just apply the simple series rules to, then we can back out and say, oh, this whole pathway is in parallel with that one. And that's the secret for dealing with complex circuits. What you do is you reduce this to a simplified version of it, where you replace R1 and R2 with a single effective resistor, right? And it has an effective resistance of R1 plus R2. And then you can think about that new hypothetical resistor as being in parallel with R3, and then you recovered a simple parallel circuit. And so that's the way you deal with combo or complex circuits. So now that we've looked at the 3 basic different types of circuits, series, parallel, and combo ones, let's look at the rules, right? So there really are only 2 rules underlying all the different ways we can solve circuit problems, and they are conservation laws, right? And they're named after Gustav Kirchhoff, who applied these conservation laws to simple circuits and came up with these 2 rules, right? And the 2 conservation laws are conservation of charge and conservation of energy. So conservation of charge gives us the junction rule, and conservation of energy gives us the loop rule. The junction rule we've already talked about, and that is that if you look at any junction in any of these diagrams, right, the current coming in, the charges per second to any junction has to equal to the total current going out of the loop. Otherwise, there will be charge being created at that junction or being destroyed, and that would violate conservation of charge, right? So that gives you this junction rule here. The loop rule is a little bit more abstract, but if you look at the heights on these, you can see what's going on. If you take your finger and you trace any closed loop, I'll do 3 for you. Let's start here at the bottom of the battery, that is the negative terminal of the battery, and trace through the energy gain, the height gain there, the height loss there, plus the height loss there, and then come back. Okay, now I've traced out a complete loop. What Kirchhoff's loop rule says is that all the voltage gains have to equal to all the voltage losses as you go around the loop. If they didn't, right, if this plus V and this minus V and this minus V didn't all add up to 0, then there would be some energy being created or some energy being destroyed, and that would violate conservation of energy. The other loop, another loop you could do is take through R3. So go through here, you got the same plus delta V. Don't choose that pathway, instead go through this pathway. Now that entire delta V lost here has to be the same as the delta V going up there to give us a 0 for the whole loop. Here's the most interesting one, right, that people don't think of at the beginning, but there's a third loop buried right here. I go start at this junction, go down this one, right, lose some voltage, lose some more voltage, and now I have to trace, and I'm going up the hill, right? And so my finger, not the charges, but my finger as I go around this loop, loses 2 voltages here and gains 1 there, and they all have to add up to 0, right? Which you can see on this diagram, right? If I climb up the hill here and then I go down the hill through these 2 paths, of course, the change in altitude has to be the same. And you could trace your finger the other way too. It doesn't matter, right? The loop rule doesn't care which loop, as long as you complete a full loop and you keep track of your plus and minus signs as you go up and down, Kirchhoff's loop rule has to be obeyed, right? So these are very abstract in general and always true, but here on the last slide, let me just break it down into how the rules manifest for simple series and simple parallel circuits. And this is just really the first 2 rows here, just a codification of things we've talked about several times, right? So if you apply Kirchhoff's loop rule to elements that are in series, then the voltage supplied by the battery has to be used up by the sum total of all the individual voltage drops by all the resistors in that pathway, as opposed to in a parallel circuit, each resistor is on its own path and therefore is using all of the voltage in that one pathway, right? And so that's why you get the rule that the resistors in parallel all have the same voltage as to each other and to the voltage being supplied by the battery. Now, the current also, in a series circuit, there is no junction, right? So there is no addition or subtraction of current. So everybody has to have the same current. Every single element needs to have the same current that is going through the battery, is going through all the wires. There's no split points for the current to be added or for current to leave. However, on a parallel circuit, right, each of those parallel paths has its own individual current, and yet every single charge that goes through those parallel paths had to come through the battery, right? So the battery, or the total current for the entire circuit, has to be the sum total of all the individual paths. Otherwise, you could find a junction where the junction rule wasn't being obeyed, and that would mean charges were being created or destroyed. Now, the resistor loop, which is traditionally is the thing that's taught first, is actually not a fundamental rule, right? You get these rules for resistances by using Kirchhoff's rules for voltage and current and then using Ohm's law, right? So if you stick in V equals IR into each one of these terms, you'll realize the I's are all the same and they cancel out and you get this rule for resistance. This one makes intuitive sense, right? You've got one pathway, the charge has to go through every single resistor you put on that pathway, and therefore it just gets harder and harder the more resistors you put in series, right? And so this should be really called the equivalent resistance of the whole circuit. I was a little bit lazy here, and I used the word total here, but that's non-standard, and I shouldn't have done it, right? It's the equivalent resistance. It turns out the equivalent resistance for a series circuit is the simple total of all the resistances, but it's not the case over here for parallel circuits. So the preferred term is to talk about the equivalent resistance. The way I like to think about what is the equivalent resistance of the circuit is that's what the battery actually feels, right? So when the battery is pushing out charges on one end, the battery doesn't know any of the details about like, oh, there's 3 resistors, 2 of them are in series and 1's in parallel. It just knows that there's a certain resistance to shoving that charge out of there and then having that charge, through the domino effect, pop another one in, right? And that resistance is the sum total of all of the effective resistances out here, right? And that's why we shouldn't say total, because it's not R1 plus R2 plus R3, because they're not all in series. What do you do in parallel? Well, you get this very strange formula, right? This is not very intuitive at all. It comes from substituting in this equation. Every time you see an I, substitute by Ohm's law V over R, and V over R, and V over R. And then you realize all the V's are the same, so they cancel out everywhere, and you get this weirdo, you know, the sum of the reciprocal of all the resistances that are in parallel is equal to, not the equivalent resistance of the whole circuit, but 1 over the equivalent resistance. This is the most common sort of careless error that students will do when they're solving for parallel circuits, is they'll do the right-hand side and then they'll forget to flip their answer on the calculator, right? So something to look forward to. The rule of thumb here is, you know that for resistors in series, the total, or the equivalent resistance, I should say, is bigger than the largest resistor. Over here, if you think about what this means mathematically, that you're adding up reciprocals and then taking the reciprocal of the answer, that means the equivalent resistance of the entire circuit is lower than the smallest resistor, right? When I was a first-year student and I couldn't really rederive all these on a test or something, what I did is I memorized the series circuit relationships, and then I just remembered, oh, the parallel is the inverse of all the rules, right? So current is the same everywhere for series. Voltage is the same everywhere for parallel. Oh, the voltages just add up for series. Oh, the currents just add up for series. Oh, for resistors in series, I just add up all of the resistors. Oh, for resistors in parallel, I just add up all the inverses, right? Now, this may seem unintuitive. In fact, it should bother you when I tell you the equivalent resistance of the whole circuit is smaller than the easiest one to get through. But if you think about it in terms of traffic, let me see if I can motivate this for you. Think about this as being cars that need to get home, right? You need to get home from work at the end of the day. And these are different ways you can get home. These are different routes, like your favorite shortcut, and then there's the way most people go, and then maybe there's a third one out here. You can imagine that, or adding a fourth one. As you add more and more possibilities, more and more pathways to get home, you are increasing your ability to navigate through the traffic, right? And therefore, it actually makes it easier, right? Even if there's no traffic on this road, if there's a third road out here and parallel to it, it gives all the cars that are driving along even more. Like if this guy hits his brakes here and comes to a sudden stop, you have time to go and take a different route home and avoid that stop traffic, right? So the more paths there are, the lower the resistance gets, right? And so even if this is a super low resistor, if it was all by itself and that was the only way home, that would still be harder to do than if you put this high resistance path right next to it. It gives you more options, right? And so as far as the battery is concerned, the overall ease on the traffic flow for the whole circuit, you're making it easier and easier to get around and around, even when you add a high resistor in parallel, right? I like to think of this, to me, there's an analogy here to when we talked about resistivity and the resistance of a wire, and we talked about how the resistance of the wire goes down the fatter and fatter it gets, right? The bigger the cross-sectional area. And that's because it gives that single charge more options about how to get down through the wire. So I think of that as the same idea. Okay, these are the rules, and almost any circuit that is just made out of resistors will yield itself to a careful application of these formulas. Okay, that's it.